but there is a course website. I think things are already present, or maybe not, but in any case, they will be present. We have your emails, and we will share everything. And I will share this notebook, the data, and the presentations. And in theory, I mean, a lot of you said that they have good knowledge of Python, so I guess you know how to set up virtual environments and install the packages if you want. Then you should be able to run everything. But in case, I'm keen to help you. This is the first of 4 lessons. Today we go, very, very slow and introductory. Not that later we will go very fast, but we start from the very basics. And I kindly recommend you to join the last lesson, because I find it the most important. Maybe not the most important one, because it builds on the others, but it has, it'll trigger some discussions, I think, much more than the first 3 lessons. Speaking about discussions, you can ask questions anytime you want. I think the lesson will be recorded. Okay, so let's start from what the course is about and not about. We will talk about language models. We will see later what they are. But we don't focus on other aspects of NLP which are related to language models, but the course again is on language models. So we won't delve into grammars or this. I assume you see the models as well. So we're not going to talk about sentiment analysis, part of speech tagging, these tasks that are very common in NLP. NLP is huge, and language models is a part of it. I would say lately things are also being merged a bit. You have language models that are being used here and there in other tasks. And the idea of this course is to give you the foundations. And I set it up in a way that sort of like follows a story. I'm not just going to give you notions and pieces of technology, but how things sort of evolved through the time in language modeling research. The code that you will play with, and the code that I'll show you is not optimized. Here, the focus is not on reaching state-of-the-art performance and whatnot, but just to show you how things work. And because of that, the code is a bit redundant, and that, of course, things can be done always in a better way. The most of the content that you will see is based on this brilliant book by Juravsky and Martin. It's freely available on this link. However, at the end of each lesson, I'll give you references. So what the course was based on, of course, not just on that paper, that book. I will give you further readings and maybe some other references. Something about me. This is my name, Corrado Grappiolo. I joined CeADAR a year ago, and I started playing with AI for quite a while in 2004. And then I got a PhD in computational intelligence in 2014. And I guess my research interests are these 3 mainly. One is bio-inspired approaches to AI. Computational intelligence is part of it. And I really like the idea of taking inspiration on how nature solves their problems, and then try to make pseudo algorithms that are inspired by that. I like this idea of hybrid intelligence. I don't think it's a term that I invented. I don't think I have invented anything, but by hybrid intelligence, at least I mean the idea of combining different approaches and paradigms or intelligence, if you want, together. And that could mean, using different AI techniques like connectionist and Bayesian and symbolic AI altogether, or human in the loop type of thing, and collective intelligence and whatnot. Because what I like is the idea that by combining, having systems which are more than the sum of the parts, if you want. And since my background is in evolutionary computation, which is part of computational intelligence, I like the idea of the evolution of things, how things evolved, or let's say, nowadays we have certain standard, state-of-the-art architecture in language modeling, if you want to talk about language modeling, but where does it come from? It didn't start from this architecture. So how did we get to a certain point? So I like to see how things evolved. I guess you might have seen the trailer of this course. What is required from you is not really a specific knowledge in AI, machine learning, or NLP, because the idea of this course is to give you the foundations and to let you, to have a course that is self-confined. What I would like you to do is to interact and ask questions and raise comments and whatnot. Regarding the knowledge, I had the chance to have a look at the self-reports that you filed in, and this is a bit of like a representation of it. I guess you were asked 4 questions, like your familiarity with Python, natural language processing, language modeling, and machine learning. And I have to say that there's quite few highly skilled people that enrolled in the course, that they self-report as being experts, if not, super experts in these fields. I hope you won't be too bored in this course. The camera is off, so if you fall asleep, that's fine. But maybe you can help in raising very, very nice questions. The idea of the course was intended to target these sort of people that have sort of familiarity with the topic, but maybe they don't know all the nitty-gritty details. Moving on, let's start, and let's ask what language models are. Does anyone have an idea? Maybe not the experts, but those that they're not too knowledgeable on it. Do you have an idea what language models can be, or how we can define them, or at least where they are used? No one? Okay, so we'll get there on what they are. I'll give you some example on where they are used. This is an example, Google search, that suggests some words when you type on the search bar. Another example is when you use the phone, you write text, and the phone, the app, suggests you the next word that you can fill in. And also during translations, machine learning, that models, systems that are used to translate from one language to another rely on language models. Now, what language models are, or what they are about? Language models are about generating text in the end, and the fact that text is being generated in many tasks of NLP, such as question answering, machine translation, text summarization, and dialogue like chatbots, then you can see that language models are important. Maybe they're not that evident, they are being used, but they are a core component of all these tasks in NLP. And so since it is about text generation, another way of seeing language models, or a definition of it, is the following. Models that assign probabilities to sequences of words are called language models. In a more formal way, we can imagine it as a way to calculate the probability of a word given a history, so previous words that were typed or generated. And this history is also called a context in language model on NLP, in the NLP domain. So if we look back at the search suggestions provided by Google, you can imagine that Google calculates the probability of whether given what is like it's the probability of dark web given what is possibly weather has a higher probability than weather today. So weather shows up highest in the suggestions. How do we retrieve or do we estimate these probabilities? Well, the idea is to use a data set or a training corpus, again, if we use the NLP terminology. So you will see that language models are built based on a training corpus. Okay, so far so good. So I'll give a very quick introduction to probability theory, just to have the notions, I would say, that we will use throughout the course. I guess we all know what probabilities are. You can imagine this is a simple example. You have imagine you have a dice that you roll for, what's that, 1 million times. Then we count how many times we see a certain number baby showed up, and these are the counts. And then by normalizing these counts by the total number of samples, we obtain probabilities. This is the frequentist approach to define probabilities. I don't really know the definition, I should look for it, but you have an idea. So the frequentist approach. So you estimate frequencies and count, and then by normalizing, you obtain a probability distribution. And probability distribution is such that the sum of the probabilities of all the events is 1. And probabilities are values that range from 0, the null event, to 1, the certain event. So in this case, we have the dice, we have 6 faces. So of course, the sum of all, the sum of the probabilities of all possible events is the certain event, which means that by rolling a dice, you will always get a face as outcome. These were the probabilities that were estimated from 1 million. Sorry, I forgot one just other detail. That another way of defining probabilities is the theoretical part. So the probability of a face is 1 over the number of faces. And you can see that if we see that the probabilities retrieved from the frequentist approach align very well with the theoretical definition of probabilities of these events. So we get to define the joint probability of 2 events occurring, and is defined as the sum of the 2 probabilities. So if you want to calculate the probability of rolling a dice and obtaining 1 or 2, this is the theoretical definition, and this is the definition, the value that we would get given our observation. So by rolling that 1 million times the dice. The joint probability is the probability of 2 events occurring, and it's calculated as the product of the 2 events. So imagine we want to roll the dice twice, and we want to calculate the probability of observing 1 and 2. This is the probability of that. And then the last bit, it's the conditional probability, which is the probability of an event occurring given that another event has occurred, and it's defined as the joint probability of the 2 divided by the probability of the prior. This is the prior event. And in this case, imagine we want to roll the dice twice, and we want to calculate the probability of observing 2, given that in the first time that we roll the dice, we obtain 1. We obtain that the conditional probability of 1, the conditional probability of 2 given 1 is the same as the probability of 2. In this case, we say that the 2 events are, the event A is conditionally independent on B. But we are not going to go any further into that. So as long as you know this is the notion, the conditional probability, then you should be fine in understanding the rest of the course. Now, any questions so far? Then we can move on and talk about n-grams, which are arguably the simplest approach to language modeling. Let's recap again. The idea of language modeling is creating a model that can calculate the probability of a sequence of text, or probability of a word given a previous a context. And a sequence of words can be represented as this chain of words from 1 to n, or in a short notation, we can use the colon. So the idea, given a sequence, the probability of a sequence, so the probability of all the words from 1 to big N, is the product of the first word that was seen times, so joint probability, times probability of the second word given the first word, times the third word given the first two, and so on until the last word given the full history. And this can be represented by this big product symbol. And if we manage to do that, then we are fine. We have our language model. But things are not that simple. First of all, because new sentences are always generated, so we have new combination, new words. So we need to recalculate these probabilities every time. We said new sentences, so there might be new words that we have never seen before. The sequence can be very long. I counted how many words there are between things and this number 34, which are 34 words. And you can imagine that calculating the probability of a sequence of 34 words, where each probability value ranges between 0 and 1, can lead to underflow calculation. So this is also a problem when we want to use computers to calculate this probability of sequences. The n-grams was, I suppose, the first approach to try to tackle all these problems, yet to be able to calculate the probabilities of sequences. It's based on the Markov assumption, so-called Markov assumptions, because Markov introduced it. I think he introduced it in 1913 even, when he was, I think, also thinking about probability of sequences of words. I'm not sure about that. In any case, I recommend you, at the end, I will show you the references I said. And in that Juravsky-Martin book, there is the historical remarks at the end of each chapter, which I think it's brilliant. Anyway, the Markov assumption essentially is a way to overcome the problem of calculating the probability of a full chain of words. And it's defined as, can assume that the probability of a word given the full history can be approximated to the probability of that word given a limited history. And that's the Markov assumption. And once if we rely on the Markov assumption, then we can build our n-grams. And this is based from extracting frequencies in given a training corpus. So it's very similar to what we did before with rolling the dice. And the idea is that we can calculate the probability of a word given a limited history as counting how many times the full sequence has been seen, as you can see from the whole history plus the word we want to predict, divided by the full history. So that's the condition probability formula that you saw before. And in this way, we can see that if we go back to the Google example, the probability of whether given what is there, you can assume that Google has this giant data set with all the search strings that were submitted. Google can calculate the counts of how many times what is the weather was typed in, divided by how many times what is the was being typed in. And then the probabilities are retrieved. Bit of terminology, depending on the history, we have a different way of naming these n-grams. If we don't use a history, so we have unigrams, so we only calculate the probability of one word given no context. Then we have bigram if we have a history of 1, 3 gram for history of 2, 4 grams, and so on. And in n-gram modeling, all words are unique. So imagine a word and the plural or synonyms. These are all treated as unique words. That's the simplest way of using n-gram models anyway. Although n-grams are very simple and straightforward, or maybe because of that, n-gram models are extremely explainable, because it's to some extent it's a way to summarize a corpus. And not only they're explainable, so it is possible to directly retrieve why a certain n-gram has a certain probability, but they are also easy to visualize, at least for n equal 2. So when we use bigrams, so basically we have the probability of a word given the previous word only. This can be visualized with graphs, where we have a word, the previous word is the one before the arc that connects the two. And then we have also probabilities. These models, although they're very simple, and because they are very explainable, can also reveal a lot of information of the training corpus. And this is an example, comes from a work that I've done quite back in the past. It was a project in which we worked on medical machines. We were collecting, there were log data. They were logging, these log data collected events regarding how the machines were being operated in hospitals. And the question that we tried to answer in this project was, how are these machines used in the hospital? How in different ways are these machines used? Because you can imagine that doctors with different backgrounds use the machines in different ways, depending on the patient, depending on the severity of the disease that this patient has. Machines are used in different ways. So what we did, we took all these logs, we created n-gram models, and then we presented these models that basically represent ways of different medical exams. We presented them to domain experts, and domain experts, by looking at these graphs, they could understand the type of examinations that was being performed on which patient. So although n-grams are very simple, they can be very, very powerful. Now we can get a bit on the practical bit. We will use a data set of recipes throughout the whole course. And for this example, for n-grams, we will use 5,000 recipes, and we will focus on unigrams, bigrams, 3 grams, and 4 grams. This is an example of a recipe that you will see. I've done a very, very basic cleaning procedure, which basically means I removed all punctuation. Everything is as low caps, and I removed all the numbers, and I used this token. But apart from that, I guess you can read this recipe, right? So this is an example. I used this was the formula used to extract n-grams, and we can see an example. So if we want to see the unigram of garlic, we have these values. So that means that in the whole corpus of 5,000 recipes, garlic was observed 301 times, and this is its probability. This probability is calculated according to this formula, and you can see it in here. So we have, in the whole training corpus, we have nearly 4,000 unigrams, so 4,000 unique words. The total number of words in the corpus is nearly 254,000. So the probability of garlic, given no context, unigrams, is the count, 301, divided by this value. So that's how we get the probability of the unigram probability of garlic. But then we can go and see the bigram. So this shows the probability of onion given garlic. So onion, so in the text, there was the ascent, 3 times in the text, we had a sequence of garlic onion. Probably there was a comma somewhere, but as I said, I cleaned the text, so it went away. That's why it doesn't really sound good in English to say garlic onion in a recipe. But then you can see that garlic is then followed by in 36 times. There is powder that is very frequent, and so on. We have also 3 grams. So if we can go further, we can go and see garlic powder. See that after garlic powder, there's usually a new line comment. That's another token that I introduced to show that the recipe has been split into instructions. Then we have also the 4 grams. So we can add new line. We can add salt. Let's see what happens after salt. After salt, we see that there is also oregano, and things go on. Now, we said that language models are used to generate text. So let's try to generate text. How do we generate text given n-grams? Well, the idea is to treat these n-grams as a probability distribution and then sample for it. So we can take as an example time. So we want to get the bigram probabilities of time. So what follows time are 1, 2, 3, 4, 5, these 6 words. And this is basically the probability distribution of the words that follow time. So the words conditioned to time. And the sum of all these probabilities is 1. This is the cumulative probability of the words that are conditioned to time. So since we have a probability distribution, the integral is 1, that's the certain event. What we can do is sample a random number between 0 and 1, and then obtain the probability related to that interval. So we can try again. We can see, because if we sample this value and we obtain new line, we can do it again. We got basil, we got again, we got new line, we got and this is how basically we generate text. We can go and see other distributions if you want, and this is all retrieved from the training corpus. So we can try to generate text. We use 4 grams and we print the text that we generate based on all this continuous sampling. And this is an example of generated recipe. We can try to read it if you want. I think it sort of makes sense. Possibly, I don't know. I've never seen it before. But we can go and find it in the training corpus. So if we want, we can look how many times put peas in is present in the training corpus. We see there is only one. That's a good example, because there's only one instruction, one recipe, sorry, in the training corpus that contain put peas in. And you can see that this is the same as the first instruction. So in a certain way, the n-grams just regenerated the training corpus as it is. And we can go and look into why that happened. We can go and see, let me see, we can put this history and see what happens after peas in calendar, and there's only a new line. That means that indeed this was the only occurrence of peas in calendar new line. That's why the n-gram sort of got stuck and just parroted the training corpus. We can lower the number for n, the n-grams, and then you can see that the meaning of this, I don't know if we can use the term meaning, but that the recipe starts losing its sense. You can see in a large bowl, and then it got interrupted already. Pour into a bowl, that's also interesting. Pour into a bowl doesn't really have any meaning if you want. Dissolve. And the lower we go with the n, the weirder the recipes are, because basically the history, the context gets shortened. So to some extent, the n-gram doesn't have a memory, doesn't remember what it generated before. If you want to use, some anthropomorphization of n-grams. If we use unigrams, we basically sample single words. We have absolutely no memory. We are memoryless, and this is what we get. So with this, you should start getting an idea of the importance of n, and in a construction of a language model, or the importance that the context has in the construction of a language model, and also the relationship that exists between the model and the training corpus. We can also calculate probabilities of sequences. That's what language models are for. So we can calculate the probability of this full sentence, garlic and parsley. I think, yes, it is present in the training corpus. So that's how we get these results. And you got the formula before on how these are calculated. And what we can see is how this changes when we change. Oh, this is some spoiler for the next slide, but we can have a look at how the probabilities change given the variation. We change n, we change the history, so of course we change probabilities because the frequencies are different. This is something we should get now, I guess. Yes. So let me first go back. We see that the total probability based on 4 grams of this sequence, add garlic and parsley, is 0. But if we go and look at but here, if we go and look at the unigram probability of this sequence, we don't get 0. We get a very low value, but it's not 0. This means that all these words are in the vocabulary. So why do we get 0, although we have these words in the vocabulary? I don't know if I introduced the term vocabulary, but vocabulary is basically the unique words that are present in the corpus and therefore in the n-gram model. So how do we get 0? Well, that's because we have 2 types of zeros in n-grams. And one is when there is no co-occurrence of words, although these words are present in the vocabulary. These have never seen together in the training corpus. So if we want to look at the graphical aspect of it, that means that there's no arc connecting one word with another one. And how to circumvent this problem was a common strategy is to leave some probability for these arcs to occur. And we get there later on how we can achieve that. There's another type of zeros, which is when we have unknown words. So when there are some words that are not present in the training corpus. I mean that in the sense that you can imagine that a language model is being built on a training corpus and then is being deployed in production or whatever. And then this language model has to calculate probabilities of these incoming sequences. And it could happen that there are words that are not present in the training corpus. So how are these probabilities calculated? We don't want to return a zero. So let's go and have a look at a few methods. Smoothing is a set of approaches that try to leave some room to calculate probabilities of concurrences that haven't been seen before. So you can see the example here. This second is the log probability, so forget about that. That's a quick approach to avoid overflow. So instead of calculating the probability, the product of all probabilities in a sequence, you calculate the sum of the log probabilities. But never mind that. So you can see that sliced garlic and peppers gives 0. But if we use smoothing, and smoothing is defined as this, so it basically introduces some offsets on the numerator and denominator, I think it's called, so that non-zero, imagine there is a count that returns 0, so there's no concurrence, but because of these offsets, the returning probability is not 0. And by k, this k value is actually added here, and instead of 1, it will be 1 times k and k times v. V is the size of the vocabulary. With k equal 1, we have Laplace smoothing, and this would be the probability. Oops, sorry about that. And then we can increase k, and by increasing k, the probability gets smaller and smaller. And that's because this denominator gets bigger and bigger. Interpolation and back off is another approach. Back off, essentially means that if we don't have this order of probabilities, so the count at this order, so in this case we talk about trigrams, the count is 0, then we go and look at the lower order, so the bigram, and then we go in the lower order and we go to the unigram. And in this way, we avoid to using a 0, to return a 0, and to then use it in the probability, the product. However, if we do that, there's the risk that the probabilities are not longer between 0 and 1, or anyway, the probability distribution is no longer probability distribution because the integral is no longer 1. And then there's this other approach, which is called interpolation, and things can be put together. So basically, instead of just backing off to the higher order and higher order, we can make a linear interpolation of the 3 probabilities by a parameter lambda, with the constraint that the sum of these lambdas has to be 1. And this is an example you can get by calculating this back off and interpolation for the same sentence with these weights, lambda 1, lambda 2, and lambda 3. If we talk about out of vocabulary words, you can see this example. So we obtain 0 if we want to calculate the bigram probability of this sequence, and that's because tempe is not present in the vocabulary. That's why we obtain 0. So how do we do with that? This is an out of vocabulary word, which means that it wasn't present in the training corpus. So an idea is to introduce some unknown out of vocabulary words or let's say the idea is to convert the training corpus to make room for unknown words, and then in that way we can model out of vocabulary words. So if we can use some techniques to estimate how likely a rare word is, and in this case it's a very simple strategy that I adopted. So we look into words that occur only once in the training corpus, and then every time we observe that word, given a certain probability, we convert it into this token, UNC. In this way, when we want to calculate the probability of a sequence that contains out of vocabulary word, these words that are OOV are being converted into UNC, and then we use that probability value. And this is an example of, I don't know if you, okay. This is an example of a recipe that contains this token. We can go and look at the, let me see, we can go and look at the original recipe, which was here. It converted lump into unk. And then, of course, we can go and have a look at lump. Okay, there's only one. So this was a rare word. And then, given that very simple strategy, we convert it into unk. And then we model the probability of observing an out of vocabulary word. Yes. Now that we have, I generated some new n-grams based on this out of vocabulary, this corpus that contains unknown tokens. And this is a recipe that has been generated. As you can see, it treats the unknown token as out of vocabulary. So I don't know how meaningful it is. Nonetheless, it does that. And then we can go and look into this these tokens. So we can go and look into, let me see. This. Let's see if there is a recipe with that. Yes. There was a recipe contained cool to unk. So again, we used 4 grams. So we're very pedantic, or not, maybe not pedantic, but we're like parrots. The higher n, the more parroty n-grams are. And now that we have unknown tokens, then we can calculate the probabilities of sequences that contains out of vocabulary words, because tempe is not present in the dictionary, in the vocabulary, but yet we convert into unk. You can see it in this way. It should return the same probability value. Yes, as you can see, it's the same. And then, of course, we can do the same story. We can also use smoothing and interpolation, because we can still have a problem with the co-occurrence of words. Now, I guess we're slowly going towards the end of the lesson. I hope someone is still awake, because I haven't heard anyone talking yet. So some initial thoughts. Well, as you have seen, n-gram models, maybe like all statistical models, are dependent on the training corpus. That means that the training corpus is very important. And of course, the richer the corpus is, so the bigger it is, the more the recipes in that case, the more powerful n-grams will be. And you can imagine that if the corpus gets bigger and bigger and bigger, we might have the chance to increase n, to increase the context, because we sort of reduce the parity properties of n-gram models, or possibly of language models. One thing to take into account, since there is this very tight link between the training corpus and the n-gram models or language models, is that the probabilities encode specific facts about the training corpus. So in the end, the language model has a bias, and the bias is, to some extent, it is very related to the bias in the training corpus. So you can already think, if what problems can this bring? And there's another thing to take into account, that depending on the size of the training corpus, or the purpose that we want to make of with these language models, we need to be careful on the nature of the corpus. So this is a quote that I took from the speech, the Żurawski-Martin book, essentially, that says that to build a language model for translating legal documents with the training corpus of legal documents, this is something that is very common in machine learning, but it's good to take it into account also for language models. So with the n-gram models that we used, that we trained, maybe training is not the right term, because it's not really machine learning what I showed you, but the n-gram model that was built on recipes cannot generate legal text, essentially. And to wrap it up, we started looking into what language models are, where they are. We looked into n-gram models, which is the simplest approach. We saw a bit about the interconnection between the training corpus, the model, the hyperparameters. For the case of n-grams, the only hyperparameter is the history size. Of course, we have other hyperparameters when we talk about probability calculation, but to build n-grams, we only rely on the context size, so n. We saw how zeros exist, so we have a problem with co-occurrences and out of vocabulary words, and we saw how this is generally solved in n-grams. And then we had a look at the training corpus. The lesson is based on mainly chapter 3. I don't know, you can have a look at these 2 paragraphs that I didn't cover, and this is a link on probability theory tutorial in case you want to refresh your mind a bit more. These are 2. This is the website where I found the full data set on recipes. It's a very interesting data set, a very interesting project, sorry, because it's about generating text with partial information. So basically you go to the website and you can choose which ingredients you want to have in a recipe. And there is a recipe generator that generates a recipe based on those ingredients. I tried once and the result was not that outstanding, I would say. And with this, I'm done. So if you have any questions, let's bring it on.
Corrado, Bruce here.
Yep.
How do you deal with words that have the same letters in them, the same word, but different meanings?
Yeah, with n-grams, you don't really do that. We will see later in the course that there are new approaches that can attempt to give different meanings, and that's more on it's called word embeddings. So the idea to convert a word into a vector and then having different vectors representing the same word. So an example is apple, that can be the fruit or can be the company. So based on the context, these techniques can change the value of these vectors. But for n-grams, that's not possible.
Okay. And secondly, second question, could you, based on this work,
yep.
Sorry?
Yeah, maybe I wanted to say that unless you change the corpus yourself, that you know that there are these ambiguities in different meanings for the same word, then n-grams cannot really help you with that.
Okay. Based on the work that you've done with this recipe thing, can you create a completely new recipe, which you can then go and test in the kitchen?
Yeah, you can do that. And basically, well, one way is to where is it? Where do we generate recipes? Let me go back. Where? Yeah, well, here, by using one, this whole recipe that means nothing, it's meaningless, is not present in the training corpus. So this is a newly generated recipe. We can also actually increase n if you want. And again, this doesn't really mean anything, but I also doubt this recipe is present in the training corpus. A fun thing is that I was playing with it. Look, there is mixed, dry, and smooth. You have to find it somewhere. Mixed, dry, and liquid. So you see it's this is newly generated. It's funny that I played with it yesterday, I think, and I got as a generated recipe was something like beat it with lid until firm or something like that. That's kind of funny to imagine, you know, like domestic violence. But anyway, it was funny for me anyway.
So would it be possible to generate a whole recipe, you know, with maybe 8 steps or something?
Yeah, I mean, the code that I wrote is very simple. It generates words given that probability distribution until the end of sequence token is being found, that you don't see it here. But it is possible to generate text, you know, given constraints, or make it that long, or you know, you can add heuristics that say if you find this if you sample and you want to generate end of sentence, sorry, but we are still below the limit, then ignore it, resample, and go on. That is possible, yes.
I would be interested in getting from you, as in Word, MS Word format, say a 5 or 6 step recipe completely generated by whatever work you've done.
Like this one.
Then go to the kitchen and see what happens.
Well, the thing is that I removed numbers. So, yeah, you see, you don't know bake at, you don't know until brown. So I guess it doesn't even give you the units. So this is a toy data set just to show you how things work. But maybe what we can do at the end of the course is using more sophisticated approaches to language modeling to generate more meaningful recipes. This is also based on 5,000 recipes, and later on we will use 10,000. But of course, the bigger the data set, the more rich the recipe you can generate, I would say.
Okay. And another question, I don't know, before anybody else asks, is this computationally heavy? Like...
No, n-grams is not heavy at all. I mean, it gets heavy when the data set increases. Everything is stored in memory, at least in the code that I developed. But this runs in few seconds. I think you can run the whole notebook in under a minute, and you get all your results.
Okay.
And I'm sure there are optimized code are out there for n-grams that would be even more efficient than what I wrote.
Thanks, Corrado.
No worries.
For me, it was interesting insights that you gave. So thank you.
Thank you. That was the goal. I guess no one has other questions, so maybe we can finish it here. Okay. See you next time.